There is a pair that passes every statistical test. Mean reversion is close to guaranteed. It snaps back to equilibrium in seconds. And if you trade it, you lose money. What is certain does not pay. What pays is not certain. Today we look at that exchange rate. Last time we measured the size of the risk, the standard deviation of the differenced spread, and then the Sharpe ratio. Today the question changes. Not the size, the eligibility. This is the stationarity test for pairs trading, and it is the checkpoint that decides whether a spread is worth trading at all. There are 3 gates. The first gate: does the difference in the spread actually equal the return in your account? For 8 episodes, I have told you that the change in the spread is your profit. Honestly, we have never once sat down and checked it with real cash flows. Today we do. The second gate: is the distribution of the spread close to a normal distribution? That plus or minus 2 standard deviation entry line we have been drawing since part 3. The reason it exists is here. And the third gate, the most important one: stationarity. In the original author's words, and I am quoting him directly, the stationarity of the spread is the single biggest variable in choosing a pair. Pairs trading is only possible when it is there. And standing at that third gate, we are going to run into the most uncomfortable fact in this entire series. Let us check the arithmetic. When you enter, you buy stock A and you sell stock B multiplied by the cointegration coefficient. That moment gives you one spread value. When you exit, you get another one. Our claim, all series long, has been that the difference between those 2 values is your profit. The original author actually tested it. He took 2 points on a real spread chart, worked out how many shares to buy and how many to sell, and then computed every cash flow through to the exit down to the currency unit. Here is the result. One leg lost money, the other leg made more than the first one lost. Add them together, and you have a net profit. Divide that by the amount invested, and the realized return matched the return computed from the spread formula to the second decimal place. The theory agrees with the brokerage statement. That is what Gate 1 is for. But there are 2 things I have to be honest with you about. First, log returns and simple returns are not the same thing. The same trade came out at roughly 19.7% in log terms and roughly 17.7% as a simple return. The spread we have used since part 4 is built on logs. What shows up in your account is a simple return. So if you read a log spread value straight off the chart and call it your expected return, you are overstating it slightly. And the wider the spread, the wider that gap gets. Second, the invested capital is only the long leg. A borrowed short does not take cash out of your pocket at entry, so the denominator of the return is just the purchase amount. In part 9, I said pairs trading is already 2 times leverage. That leverage comes back here, in a different costume. It inflates the percentage, the same profit and loss, computed over half the capital. A return that looks good and a risk that is small are 2 different statements. There is one property worth stopping on before we go further. 2 prices that had drifted apart come back to the equilibrium point. But where do they meet? They can both rise and meet high. They can both fall and meet low. They can meet somewhere in the middle. It does not matter where they meet. If they meet, you make money. This is the strongest evidence there is that pairs trading is not a directional forecast. In part 1, I said we bet on the gap, not on the direction. That sentence is finished here. You do not need to know where the market is going. You only need the 2 of them to meet again. The formal proof of why that works comes in part 12, but there is a condition attached, and this one is a trap for anybody running a backtest. The equilibrium point itself moves over time. That is mean drift. So when you simulate or when you backtest, you have to recompute the equilibrium point and the cointegration coefficient every time the analysis window and the data change. If you set the equilibrium once, using the average of the whole period, and then sweep backwards through history, you are using information that did not exist at the time. Look-ahead bias. The return that comes out of that backtest will not survive contact with a live account. How we handle that problem properly is the subject of the next episode, the spread window. Gate 2. First, why we look at the normal distribution at all. Data with the character of a residual, returns for example, tends to look normal. So run that backwards. If the distribution of your spread is close to normal, that spread probably has the character of a residual. And why does that matter? Because a residual does not run away in one direction. It comes back to its mean. It does not keep climbing, and it does not keep falling, which is the entire list of things we ask a pair to do. So checking for normality is an indirect test of suitability. The direct test is gate 3, stationarity. The method is simple. Take every value on the spread chart, count them into buckets, stack the buckets as bars. Turn the whole thing 90 degrees, and you have a histogram. A good pair's histogram has 3 fingerprints. 1. The count near 0 is high. The spread spent a lot of time near equilibrium, which means the two stocks were in balance often. 2. It is symmetric, left and right. 3. The count falls off as you move away from the mean. The further from equilibrium, the less likely. And here is where the identity of that line we have been drawing for 8 episodes finally comes out. If a distribution is normal, then about 95% of the values sit within 2 standard deviations of the mean. So a spread that pushes outside of that is a rare event, and that is your entry line. The plus or minus 2 sigma band we have been sketching since part 3. That was never a convention. It was a probability, which cuts the other way too. If you draw a 2 sigma band on a spread that is not normally distributed, the 95% reading collapses. The line still gets drawn, it just does not mean anything anymore. How do you use this in practice? You can disqualify a candidate with a single histogram. Look at the 2 examples from the original. The good one. The counts cluster near the mean, and the shape is close to a bell. The spread chart is stable around its equilibrium. Nothing about this pair looks unreasonable. The bad one. The counts near the equilibrium point are very low, and most of the mass sits far away from it. What does that tell you? It tells you these 2 stocks were almost never in balance. They spent most of their time apart. Look at the spread chart and you see it. Weak pullback to the mean and long cycles. That pair is unsuitable. One more thing. The distribution changes with the analysis period. 600 days gives you a different picture than 300 days does. But the original author's standard here is a good one. If a spread is stable, it should look roughly normal over any window you pick. If it only looks good over one particular period, the odds are you picked the pair wrong. Your eye is usually enough, but let us look at how you confirm it statistically. It is worth doing once. The method goes like this. For each bucket, compute how many observations a normal distribution says should be there. That is the expected count. Compare it with the count you actually observed. Small differences mean you are close to normal. Large ones mean you are not. Whether the difference is statistically meaningful is what the p-value tells you. A few spreadsheet functions will do it. The original author ran it on 600 days of one pair's spread. The result, a p-value of 0.18%. That is smaller than a 5% significance level, so the conclusion is that we cannot call this distribution normal. The left side of the histogram sat well away from the normal curve, because for one stretch of time one of the 2 names stayed persistently undervalued, and then comes the reversal. He ran the same pair again, not on 600 days, but on the most recent 300. The p-value came back at 26.59%, far above the significance level. This time, it is normal. 300 days is about 14 months. That is not a small sample. So, his conclusion reads like this. Over the long run, the divergence has no normality. Over the short run, it does. Remember what we learned in part 8. Change the ruler and you change the answer. Here the ruler was not a formula. The ruler was the length of the window. So how do you actually decide? His rule of thumb is practical. If both the long window and the short window pass, obviously that is the best case. If only the short window passes, that is workable. There is no real obstacle to trading it. But if the long window passes and the short one fails, be careful. That combination carries near-term risk, and the spread will probably take a long time to converge. Gate 3, stationarity, and this one is a necessary condition for pairs trading. Put 3 time series side by side, and the concept lands immediately. First, a stock price. It trends, up or down, it does not matter. We call that a non-stationary series, a random walk. Second, returns. No trend at all. They oscillate around a mean with a fairly constant amplitude. That is a stationary series. The formal definition, a stationary series has the same probability distribution no matter which stretch of it you cut out. Same mean, same deviation. Third, our spread. And this is the important one. The spread sits in between. It is not fully stationary and it is not fully non-stationary, which lets us define what choosing a pair actually is. It is measuring where your spread sits on that ruler. The closer to the stationary end, the more suitable. The closer to the non-stationary end, the less. You can see a fair amount of it with your eyes. Even when the amplitude is large and it crosses the mean only rarely, if it oscillates up and down without a persistent trend and eventually comes back to the mean, you can treat that as reasonably stationary. The standard tool for measuring it is the ADF test, the Augmented Dickey-Fuller test. The theory behind it is beyond the scope of this series, so I'm going to give you only how to run it and how to read it. You feed in your spread values and you get two things back. The test statistic, the more negative it is, the more stationary. And the p-value, if it is below your significance level, you conclude the series is stationary. There are spreadsheet add-ins for this, and in Python it is a single line. Here is what the original author's data showed. Returns came back at a p-value of about 1%. Stationary, confirmed. Stock prices came back at about 37%. Not a stationary series. The two ends we pinned onto the ruler, now with numbers on them. And let me be precise about one thing. The original says a p-value of 1% means the series is stationary with 99% probability. As working shorthand, that is fine, but strictly speaking, the p-value is not the probability that the series is stationary. It means the evidence against the assumption of non-stationarity is this strong. Mistake that for a probability and you will size your positions wrong, so today we say it the accurate way. So, the answer to this cold open. The original author ran the ADF test across a range of spreads, and the pattern in the results is unmistakable. The spread between an index future and the index itself, a p-value of 1.9%. It passes comfortably. The spread between a currency future and the spot rate does the same. Why do these come through so cleanly? Because the relationship between the two objects is extremely tight. They are very nearly the same thing, but it is precisely that reason that produces the second fact. The amplitude of the spread is only a couple of percent, and it oscillates on a scale of seconds and minutes before snapping back to equilibrium. And there is your answer. When the amplitude is that small, once you have paid commissions and slippage, there is essentially nothing left. Which is why this territory belongs to institutional algorithmic trading, where the cost of doing business is close to zero. Computers entering and exiting on a scale of seconds. An individual can build the same system and still not clear a profit because the swing is simply too small. It is certain, and for an individual, it does not pay. So what about spreads between individual stocks? In the original's examples, one stock pair came back at 10.7%. At a 5% significance level, that fails. And here I am going to repeat, word for word, a sentence the original author wrote himself. In fact, when you set the significance level at 5%, there are not many stock pairs whose spread passes the ADF test. That is the uncomfortable fact of the day. Apply the textbook standards strictly, and there are almost no stock pairs left for an individual to trade. Most content that introduces pairs trading will never say that sentence out loud. I am saying it, and you cannot pick your way around it by sector either. In his examples, two domestic retail names came back with a p-value of 78.5%, no stationarity whatsoever, while another pair from the same sector passed at 4.35%. In part 2, I said that JP Morgan and Goldman Sachs do not look alike even to the naked eye. This is the quantitative version of that. So the real choice in practice looks like this. You lower the significance level from 5% to 10 or 15. Now you have candidates. In the original's phrasing, you can regard the series as stationary with 85 to 90% confidence, so pairs trading becomes possible. As I said earlier, that probability language is loose, but as working intuition, it holds. It is not free, though. Two costs come attached. 1. More risk. The chance that it never comes back is now materially larger. 2. More time. Convergence to the equilibrium point takes longer. And there is a payment in the other direction. The amplitude is larger, which means the expected profit is larger. That is the core of today. Certainty and payoff run in opposite directions, and it is not a coincidence. The stronger the force binding two stocks together, the more certain the mean reversion becomes, and at the same time, the shorter the distance they can possibly travel apart. Two faces of the same cause. So the question changes. It is not, can I find a certain pair? It is, how much certainty am I willing to sell? Let me pull it together. 3 gates. 1. The difference in the spread really does match the return in your account. But log returns and simple returns are not the same number, and because the capital base is only the long leg, leverage inflates the percentage. 2. A good spread resembles a normal distribution, clustered near zero, symmetric, thinning as you move out. That was the basis of the 2 sigma entry line all along, and the distribution depends on the window. The same pair had no normality over 600 days and normality over 300. 3. Pairs trading is only possible where there is stationarity. Prices are non-stationary, returns are stationary, and the spread sits in between. The ADF test tells you where yours sits. And the single most important sentence today: the pair with perfect stationarity is not yours to trade, and the pair that is yours is not perfect, which is why pairs trading between individual stocks is a strategy that plays for long-run convergence. Expecting the spread to close in a few days is the wrong expectation. Waiting is part of the strategy. I will close with the original author's own advice. Through real experience, work out the level of risk and the significance level that suit you. The right answer is not 5%, and it is not 10. It is the point where you can actually pay the price. Next episode, we go after ways to reduce that price. What is the optimal way to set the cointegration coefficient? Where do you draw the entry line so expected profit is highest? And the homework we left behind today. The problem of an equilibrium point that keeps moving. That one is called the spread window. The profit profile and the lower entry bound that the advanced series promised in its introduction both arrive there. One last thing, and I mean it. Today was about how to test a pair for statistical suitability, and it is not investment advice. Every stock, every pair, and every p-value here comes from the original author's data and exists to explain a concept. It is not a general law, and it is not a backtest. And passing a statistical test does not stop you from losing money. The final judgment is always yours. If this helped, a like and a subscribe go a long way. And tell me in the comments, how much certainty are you willing to sell? See you in the next one.